Hi, my name is Finest Stribling, and this is kind of a different talk than what you guys are going to normally be seeing today. But first and foremost, I'd like to thank Ms. Johnson for giving me the opportunity to present my research and kind of what I do in my occupation. So, like I said, my name is Finest Stribling. I am a research assistant at the University of Texas at San Antonio in the physics and astronomy department. And while I'm also a physicist, just a little extracurricular, I'm also a personal trainer. So I like to stay active and work out and stuff like that. So my initial background, I am from Nashville, Tennessee. In high school, my focus was criminal justice, and the plan was at first to go to school, get a degree in criminal justice, and work in the forensics, um, maybe in the forensics department at a police department, and work with forensic science and all that kind of cool stuff. But senior year, I took a physics class senior year of high school, and it kind of changed everything for me. And so now I'm trying to pursue a career to become a professor and do research and also teach at a university. So how did I get to where I am? So when I finished high school, I did my undergrad. I went to University of Missouri, where I got my bachelor's in physics and astronomy with a minor in mathematics. And I also had an emphasis in astrophysics. So once I graduated with my bachelor's, I applied for grad school. I actually did a semester at the University of Missouri, and then I transferred to University of Texas San Antonio. And to do that, you have to apply for grad school, you have to get accepted. And then once you apply for grad school to become a research assistant, you have to also apply for assistantship. My path was a little different because I did research as an undergrad with my current supervisor at the University of Missouri. And then when she got an opportunity to go to UTSA, I also followed and moved to UTSA as well to continue my assistantship with my supervisor, Dr. Angela Speck. And the program I'm at UTSA is a dual program. So I came straight out of my bachelor's, and I'm going to be receiving my master's and my PhD in this single program. And so a couple things that people don't know, an assistantship is similar to a scholarship, to where they're paying for my tuition, and I get a monthly stipend because I'm technically a faculty of the university. So it's kind of like a scholarship, how that works, where, it's pretty much a job. And what a lot of people don't know is there's a high demand for physicists in the academia and the job industry. And at UTSA, 90% of its graduates get a job within their first year after getting their degree. So very high demand. It's a very good industry or section in science that if it interests you, it could potentially be an option. Some expectations versus reality, especially in grad school, especially more specifically getting into research. You expect to have a good understanding of the topic you choose to do your research in. You expect to jump straight into writing a paper, publications, or starting an experiment for people that do hands-on labs. You expect fast progress, things to go pretty smooth, and simple steps to get to the finish line. That's what you would expect. But in reality, especially for me, you'll have little to no knowledge of the topic that you end up researching. When I first started my research, which I'll get into a little bit of what it's on, I had no idea what any of it was. When my supervisor was explaining it to me about what I would be doing if I decided to do research with her, it was almost like a foreign language to me, even though it was still physics. There's a lot in the very beginning. There's a lot of fundamental reading. Majority of it at the very beginning is just reading, because you have to teach yourself a lot of this stuff, especially if your core classes that you take in the beginning aren't going to really dive into what you're researching. So a lot of stuff is just reading research papers and stuff like that to help your knowledge and what you want to go into research. And the process is slow. The progress is slow. Because since you have to do a lot of fundamental reading at the beginning, that means that you're not actually working on a project or looking for data or looking for this. You're just understanding the basics at the beginning. So you're not making much progress in the beginning. And then when you do start to make progress, you have to make sure you're doing things right. And sometimes that takes time to make sure things are done right, or you have to take a pause with your observations or experiments. You have to take a pause in that and go back into reading if there's something that you're not understanding. With that, you have to multitask. You'll have to do a bunch of things at once. Not only is when you're a research assistant, you have to keep your grades up. So not only are you doing school and class, but on top of that, you might have to write a paper or proposal for a grant, at the same time write an abstract for a conference presentation, and you also have to be making progress on your project or research all at the same time. So you have to be able to multitask, have good time management, and just make sure you're on top of everything that you're supposed to be on top of. And the steps can get complex. Kind of with multitasking, you could be going forward in a paper, then realize something doesn't work out, so you have to backtrack. Or if you're trying to figure out a certain data point in an observation, but it's not right, then you have to go back and see where you could be messing up, all kinds of different complex steps that could be going on with your research. And that's the reality of it. It's very, for the most part, for most people, it's very volatile. Very rarely does everything go smoothly the way you want it, but that's a part of research. You kind of live and you learn, and that's kind of how you develop as a researcher down the road. So attributes of my, for what I do specifically is data mining. So I'll get into what I specifically do a little later, but I have to look at a lot of data, and I have to go digging for data, because a lot of the stuff I'm looking for isn't just on one nice paper for me. So I have to go into NASA databases or different databases on stars and stuff like that. And I have to dig out the data myself, which is called data mining. And then once I get that data, depending on what I'm trying to do, if I'm trying to plot the temperature of a star versus the luminosity of the star, then I have to go into Excel, Google Sheets, or Python, which is a part of a coding or modeling language. I have to go in and plot it myself. So I have to analyze that data so I know what I'm looking at and stuff like that. And then that gets into the next point, coding and modeling, which the level of coding and modeling also depends on what you're doing. For what I'm doing, I don't have a full comprehensive understanding of coding and modeling, but I know just enough to get what I need done, if that makes sense. But depending on what some people do, you need to be fluent in Python or R, different coding and modeling languages. And for what I do specifically, you need to have a good understanding of physics, chemistry, and mathematics. Those three are really important, and to have a fundamental understanding of how all those work so you can explain what you're, or know what you're looking at. So getting into what I do specifically in terms of my research is I focus on the big pictures. I focus on stellar evolution, which is basically the life cycle of a star. So as you can see here, you start off with a nebula or a cluster here. And then as all of this dust and particles and stuff in the nebula start to come together, they get heavier, gravity starts to take over, and it starts to turn to a protostar. And then eventually all that mass will collapse and become, will come together and become a main sequence star. Then from main sequence star, they will transition to a red giant. And depending on the mass, it would either explode to a supernova or it will become a planetary nebula. And that's one thing that I will focus on a little later. And then from planetary nebula, you can go into a white dwarf, and that can turn into a black dwarf, supernova, neutron star, black hole. Now, here's what's called a Russell-Hertzsprung diagram, or HR diagram. And it's basically a graph of temperature versus the luminosity of the star. So here you have the luminosity, which is basically how bright it is. And here you have the temperature. And so as you can see here, this is the main sequence. Is about, our sun is a main sequence star. And that's just I'll get to what that is later. And so this is the track that our sun will take in its lifetime on its way to its death. So right now it's here, and eventually it'll get up here to a giant. It'll come across here, and then it'll go into a supergiant, AGB. It'll transition to a planetary nebula, and then it will eventually become a white dwarf, and it will continue to cool all the way until it's no longer, you're no longer able to see it, or black dwarf, brown dwarf. And so getting it to that first stage, this is where we kind of have, for me, I have to understand what happens at each stage, what's happening within the star. This is where you get into the chemistry of what's happening on the molecular level, or into your molecular physics. So in a main sequence star, you have hydrogen that's fusing in the core. And the reason why our sun pretty much stays the same size it is because the outward pressure of the fusion is equal to the gravity pulling it in. And that's how our sun is able to stay the size it is for the most part. Now, eventually, the helium in the core will run out. You only have so much helium in the core. Now, when that happens, we're going to have, I said helium, I'm sorry, hydrogen in the core. You only have so much hydrogen in the core. When that happens, helium will be the composition of the core, because when the hydrogen burns, imagine this is hydrogen, as it burns or as it fuses, it creates helium, and that helium is a heavier element. So it will start to move its way towards the center of the star. And that's how, once the hydrogen is done, you have a helium core. Now, this is where we will transition to a red giant. We have a helium core, and there's going to be a shell of hydrogen still outside of it. And that this will be where the hydrogen is going to burn. The helium isn't fusing in the core, not yet. But you will have a shell of hydrogen gas outside the helium, and that's what is happening in the fusion. Well, with this hydrogen burning shell, or this hydrogen fusing through the shell, it's a more energetic fusion, so it will cause the star to expand. And when the star expands, it will also cool, but it's going to expand a lot. So to show you guys, this is to scale. This down here is the size of our sun right now. We all know, the sun is the biggest thing in our solar system. It's huge. You could take all the planets in our solar system, put them together, and the sun is still way bigger than that, right? So you see right here, this is our sun. Well, when it turns to a red giant, this is how big it will be. So it's going to be massive. Our sun will probably get about anywhere, probably around Mars's orbit. So it will engulf the Earth, but don't worry, because we got a few million years before that happens. But our sun will expand, and it will engulf the Earth and give about out to Mars orbit. And it will pretty much destroy our solar system. But don't worry about all that. We got a long time. None of us will be here for that. Anyway, then after that, we get into the horizontal branch. Now, going back, so you can see this track right here. This is the horizontal branch. And the reason why it's called horizontal branch is because it's going to move horizontally across the HR diagram. So if you take a look at what that means the luminosity is staying consistent because it's moving laterally, right? But the temperature is increasing. So in the horizontal branch, the luminosity or the brightness stays the same as the temperature increases, right? So that's where we get this. So here we have a helium burning core. So the helium is actually fusing now. There's a helium fusing core, and that helium is dumping carbon or oxygen in the center, and it's going to begin to build up. And then outside the helium core, you're going to have a helium shell, a hydrogen shell, and then the envelope is just the rest of the star. And so, like I said here, we're getting hotter temperatures. Now, from the horizontal branch, we get to the asymptotic giant branch. Now, the reason why it's called the asymptotic giant branch is because this curve right here is an asymptotic curve. And that's where it gets its name, because it's taking that track along the HR diagram. Now, what's interesting about these stars As you can see, the radius is just as big. Here we have a carbon oxygen core, no fusion here. It's just a solid oxygen carbon core, no fusion going on. We have a helium shell that's fusing, helium layer, and we have our hydrogen layer. And all of this is right here. And the rest of this is just an envelope, a hydrogen envelope. So here's the core right here. And inside this, you have this composition, as you can see. Now, what's interesting, or what's interesting to me and pertaining to my research, is that this in the AGB phase, that's where it loses the majority of its mass as it's continuing its life cycle to death. And it will lose a ton of mass to eventually it becomes a planetary nebula. So at this point, it's lost so much mass that gravity can no longer hold it together. And so the AGB's exposed core is at the center, and all you're left with is an expanding shell of the star, the mass of the star. So all of this is just going to expand out, and you're just left with the exposed core. And so this core gets really, really, really hot. So we go back to the HR diagram. So you can see planetary nebula, you started here, we're here 5,000, 6,000. Planetary nebulas can get all the way up to 20, 30,000 Kelvin, which Kelvin is 30,000 Kelvin is extremely hot. It's hot enough to where it actually begins to ionize the gas around it. And that's getting into a little bit of chemistry. So without going too crazy in depth with too much science, just know that it's getting so hot that it's beginning to change what's going on with the dust and the gas around the star. So saying all this, give you the background information to pretty much set you up to what I do even more specifically. So I look at these two particular phases in a star's life. And by the way, it's called planetary nebula. It's not a planet. It's just when it was first discovered, it had a planet-like look, so they call it a planetary nebula. But it is it's a stage of a star's life. But I look specifically at the AGB phase and the planetary nebula phase. And what's really interesting is you can kind of see here that there's these clumps. These are clumps of gas, molecular gas, right? And these clumps are in highly ionized or really, really hot regions. It's so hot that electrons are literally being taken off of these atoms. That's how hot it is. But this molecular means that they're not ionized. So for some reason, in these regions that they should be ionized, they're not. And what I do specifically is I'm trying to figure out how and where these clumps of molecular hydrogen come from. And so the key to that is in the stage right before planetary nebula, the AGB phase, because there's these things called maser emissions, which are kind of like lasers, like a laser pointer, if you could imagine. It's kind of like that, but they're giant. If you could imagine a giant blob, a giant clump of just a big laser, kind of like that, but it's in a different, it's a different form of light. It's in the microwave instead of visible light, like you would a laser. But these maser emissions are thicker, they're big enough and they're dense enough to potentially, as the star evolves from AGB to planetary nebula, they could potentially help these molecular gas survive the ionization front. That's the theory. And I could talk 2 more hours about the specifics and details of that, but I'm going to spare you guys with all that and kind of just talk more about the logistics of how I go about that. So how do astronomers and astrophysics study faraway objects? Like I said, these objects are far away. Even the sun takes 8 minutes by traveling the speed of light. It's far. And this particular nebula is the Helix Nebula. I believe it's light years away. It's very far. These things are very far, but how do we know how big they are? So, well, light is everything in astronomy. We can't go out and get a test tube of the sun and test it to figure out what it's composed of. That's just not, it's not possible. It's too hot. We can't go to Pluto. Well, we can't send people to Pluto or people to the next galaxy and study those stars and things like that, is because it's not practical. So light is literally everything to astronomers. Just with the light we receive from stars, we can tell its magnitude, we can tell its temperature, the color of it, how far away it is, the molecular composition, the mass, and many, many more things. Just like this HR diagram that I keep referring to. This is a pivotal in astronomy. All of this is based on the light that we see. You can tell, we know that our sun has hydrogen fusion because of the light. We know red giants have helium in their core and all that stuff because of the light we see. We can deduce what elements are present, what elements aren't. We can pretty much figure out everything we need to know about stars just from the light we see. And that's why light is so important. And you have to also remember that light's more than just the light coming from light bulbs, the light coming from a computer screen or TV screen. Light is all forms of electromagnetic radiation. So you got radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. And we know about UV light because if you stay out in the sun, you can get sunburn, and that's from ultraviolet frequencies from light. Visible light doesn't give you sunburn. If visible light gave you sunburn, then you can just get sunburn from a light bulb in a house. That's not how it works. But all forms of these lights, so we can get pictures of stars in the infrared. Well, if we see stars in the infrared, that tells us something about that star. If we get stars in if we see light in the ultraviolet spectrum, then that tells us more about the star. And so we have to remember that we can use different forms of light to figure out different things. And we can collect data on that, the data on stuff like that. And so some big takeaways I want you guys to, or some advice that I would like to let you guys in on, is getting a PhD takes time. It's usually a 9 to 10 year process from bachelor's all the way to PhD. It took me 4.5 to get my bachelor's. And for this program, it's usually a 5-year program between master's and PhD for this particular program. So it's a process. It's not something that can happen quick. It's not something that you can just, jump into and expect a turnaround real quick. It takes patience. It takes time. So because it takes time, make sure you research a topic that interests you. Research is important. Research experience is important. Get as much research experience as you can as early as you can. But it's also important, especially if you go into grad school and you're doing work that's going to be the same as your dissertation. You want to make sure that that research is in a topic that interests you, a topic that you like, because that's what you're going to be spending all your time on for the next 5 years. So that's a piece of advice that I would say. And the biggest piece of advice that I think is probably the most important is don't be intimidated, especially whatever you're going into, especially if you don't have much knowledge on the topic you're getting into or the area, the field of study you're getting into. Don't be intimidated. Stick with the plan, stay consistent. And over time, once you get your foot in, you put in the time, you do your fundamental reading, you really take your time to understand the basics and work your way up to the details from there. It's all experience. That's all research is, just learning from experience. And don't let a topic intimidate you out of doing something that you really want to do. And so those are pretty much my big 3 takeaways. And I appreciate you guys for listening and watching this video. If you have any questions, this is my email, finance.stribling4@gmail.com. And this is also my website. If you guys want to check that out, I have more stuff that's a little bit more detail in my specific research and what I'm actually doing for my dissertation. If you guys want to check that out. And thank you guys for watching. And if you got any questions, again, you can email me, and I appreciate your time.